Now we'll continue to important problem in function or mapping, which is a sub-branch of abstract algebra. Here the problem is if R2 be such that fx equals to x cube, we have to prove that this map is a bijective map, and we have another problem. This problem is very important. Show that the mapping f is to R, where S is basically open interval -1 1. The function is defined by fx equals to x by 1 minus mod x. That function is a bijection. That means it is injection as well as surjection. So first we have to prove that the function is injective. Second, we have to prove that the function is surjective. After all, we conclude the function is bijective. So I'll start the problem. The first problem, say question 1. What is exactly given? It is given the function if R to R is defined by fx equals to x cube for all x belongs to R. And what I have to prove? F is injective as well as surjective. So here our first claim, what we have to prove? Here we prove that if R to R is injective. This is our first claim. So what we will do? We'll take two elements, x and y belongs to the domain, and we'll say the image is fx and fy. So what we have taken, let x comma y belongs to R, and these are basically the domain be such that fx equals to fy. So then what we have to prove for injectiveness? Fx equals to fy, start from fx equals to fy, and we'll show x equals to y. So now if fx equals to fy, fx means x cube and fy means y cube, and that exactly implies x cube minus y cube equals to 0, and that implies x minus y into x square plus xy plus y square equals to 0, and from that we can write x minus y equals to 0 because the second part in the bracket, that means x square plus xy plus y square, this is basically non-zero for all xy belongs to R. That you have to prove. So what we have to prove here? We have to prove here fx equals to fy. That implies x equals to y for all xy belongs to real number. And hence we conclude if r cube to r cube, which is defined by fx equals to x cube, this is injective function. Now we come to the second part of the problem. So now our claim is, this is the second part, that means we have to show that if R to R, this is basically surjective. So what I will do? So here the function is R to R. What is the function? The function x goes to under the map f x cube. Okay, so that means here fx equals to x cube for all x. This is given. Now for surjective, we will take a point in the codomain set. So let us choose one arbitrary point y belongs to R, and where R is basically the codomain. Now what we have to show? We have to show f of some element. This will be equals to y. Okay. So what we will take? We will take f of y to the power 1/3. We will take here y to the power 1/3. That will be y to the power 1/3 will to the power cube. So that means it will be y. And since y belongs to real number, that implies y to the power 1/3, that must be a real number, and f of y to the power 1/3 equals to y, and this is exactly holds. Thus f of y to the power 1/3 equals to y for all y belongs to R. Why? Because this y is basically arbitrary. Since y belongs to R cube, these are basically the domain set, domain R. Okay, y belongs to R cube, this is codomain, this is arbitrary. So thus, what we can say, if we take y, the p-image of y will be y to the power 1. This is also a real number. So thus, every element in the codomain set var R has a pre-image in the domain set. R. So thus, hence f of R must be R, and from which we can conclude if R cube R to R, this is fx equals to x cube is surjective. So that means this is a mapping, this is an example of a mapping which is injective as well as surjective. Now we will continue the next question. The next question is given fx equals to x by 1 minus mod x, and we have to show that this function is bijective. So what is exactly given? Our next question. So this is the answer, this is the solution of question number 2. Here, if R to R is defined by fx equals to x by 1 minus mod x for all x belongs to R. What we have to show? We have to show that f is bijective. So that means step 1, what will step 1? Step 1 will be, first we have to show that if R to R is injective. This is our first work, injective on R. That we have to show first. Okay. And for that, what we'll take? We'll take, select, and what is given? This is not R to R. This is given if S to R. S to R. This is S to R. What is S? Where S equals to all those x belongs to R such that minus 1 less than x less than 1. That means this is basically open interval minus 1 1. So let x comma y belongs to S be such that fx equals to fy. Now what we have to show? Then that fx equals to fy, if it implies x equals to y, then we can prove it is injective. So now fx equals to fy, that means x by 1 minus mod x, this is equals to y by 1 minus mod y. Now from that we can write x minus y, that will be x into mod y minus y into mod x. And in that case we have to prove here x minus y equals to 0, since x into mod y minus y into mod x, that will be 0. But the question is why that will be 0? Why this value will be 0? How to prove it? For that case, I will give you here the supportive argument why this is true. This is true because the condition, if we take, let x greater than 0. If we take x greater than 0, then what will be our fx? Our fx will be x by 1 minus x. Let x greater than 0, then fx will be x by 1 minus x, and that will, in that case, the range of fx will be 0 to 1. And let x less than 0, then fx will be x by 1 plus x, and in that case, the range of fx is minus 1 to 0. If we take x equals to 0, then fx equals to 0. Now, if fx equals to fy, in that case, x by 1 minus mod x, that will be y by 1 plus mod y. And from this condition, we can write x and y are either both positive or both negative, or both negative. So in that case, you can think about x greater than 0, y greater than 0. That means you can think about two cases. Case 1, 0 less than x comma y less than 1. And case 2, your case 2 will be minus 1 less than x comma y less than 0. In the both cases, you will see x into mod y minus y into mod x, that will be 0. That means x equals to y. So what we have proved here, we have proved fx equals to fy, that implies x equals to y. Now since xy belongs to s, this is arbitrary. So therefore we can write fx equals to fy, and that implies x equals to y for all xy belongs to s. And hence our conclusion is f s to r, this function is injective. Now we come to the second part, step 2. What is step 2? Here we have to show that f s to r, this is basically surjective. That we have to show. This is a surjective function on R. So what we'll take the element in the codomain set, say let y belongs to R, and this is basically the codomain. Then what we can write, y by 1 plus mod y, this is basically belongs to S. And if we take the image of this point, why it is belongs to S? Because y by 1 plus mod y, this is basically belongs to minus 1 to 1 for all y belongs to real number. So now if we take the image of this element, that will be y by 1 plus mod y, x by 1 minus y by 1 plus mod y. Because our function is f of x equals to x by 1 mod x for all x belongs to R. So if we simplified it, that will be y by, this will be the mod, that will be y by 1 plus mod y by 1 minus mod y by 1 plus mod y. Why? Since 1 plus mod y, that mod will be 1 plus mod y, as 1 plus mod y, this quantity greater than equals to 0. And we know mod alpha equals to alpha for all alpha greater than 0. And also we know mod of beta by gamma, this is equals to mod beta by mod gamma. For all beta gamma belongs to real number. So again, from the simple calculation, what we can write, that will be y by 1 plus mod y minus mod y. So that means it will be y. So what we get here, f of y by 1 plus mod y, this is basically y, where y by 1 plus mod y, this belongs to open interval minus 1, 1. That means S. So that implies y by 1 plus mod y belongs to S is a preimage of y. So thus what we can conclude, every element in the codomain set R must have a preimage in the domain set S, and hence if S to R is surjective. Now what is our conclusion? Since if S to R is injective as well as surjective, so if S to R is a bijective mapping, so this is a bijection.